It's also my pleasure to introduce Thomas Paradowski as the second speaker of today's seminar. As I already mentioned, Thomas is a former PhD student at the University of Wuppertal, and he's now working there as a postdoctoral researcher. And yes, it's also my great pleasure to welcome you to today's talk, especially in the light that I was one of the reviewers of your PhD thesis last year. And for that reason, I'm looking forward to your talk on the observability analysis, and especially with the implementational aspects on interval analysis. Please go ahead, Thomas.
Thank you for the introduction. And since I'm here to talk about the algorithm, let's start with a short motivation and the question what to expect of an algorithm. Well, of course, there is the obvious reason. We want to check or verify the observability of a nonlinear function, but it would be of interest if, for example, not every state of the nonlinear function is observable, to identify which states are exactly observable. And in a case that the system is not observable, to identify why the system is not observable and get an insight on what to maybe change in the output and in the sensors to achieve this observability. And for this, my talk is structured as follows. First, I will shortly talk about the problem formulation, then a bit about global observability and construct the algorithm. And then I come to the algorithm itself and talk about some examples which I will show. So the systems we are dealing with are nonlinear uncertain systems with these uncertainties alpha and beta. These can be of arbitrary dimension. And I will show that the algorithm can also deal with these uncertainties, but for now I will ignore these uncertainties and only explain the algorithm and come at the end of the talk back to these uncertainties. So how do we verify the observability for this system? A very basic approach would be to linearize the system in a certain point, construct the observability matrix, and then, for example, use the Kalman rank condition and verify whether the rank of this observability matrix is equal to the number of states. If this is the case, then Q, or the observability matrix, is full of rank, and therefore the system is observable in X0. We could construct an algorithm that tests every point of a definition area of this nonlinear system by, for example, using intervals. And in that case, we could prove that the system is local observable. However, we are more interested in the global observability. And in order to test these, we already seen this in the previous talk by Herrn Tipken. And there we, for example, take one point of a system, Z1, and have its corresponding trajectory, and another point is Z2 and also the corresponding trajectories. But this happens hidden inside the nonlinear system. What we see is the mapping of these trajectories in the output. And now we can compare the output of these two states. And if these are distinguishable, we get a definition that says let t bigger than 0. So if two states Z1 and Z2 out of a set are called indistinguishable on an interval, if the corresponding trajectories of the output match, that means that the trajectory of this output is equal for all t. Otherwise, these states are called indistinguishable or are called distinguishable. In the case up here, these two states are distinguishable because we can distinguish the outputs. Now we could, of course, do this for all states of our definition area. This leads to the definition of global observability. And therefore, a system defined on the subset dx is global observable if and only if all pairs Z1 and Z2 are distinguishable. This leads to two sets with set M, which contains all pairs for which the trajectory or the mapping of a trajectory is equal. And a set D, this contains all pairs where the states are equal. And if we can show that these two sets are identical, such that M is equal D, then we have global observability. Now we have to verify that the trajectory or the mapping of a trajectory is equal. For that, we use the Taylor series and the Lie derivatives, like shown in a previous talk, and construct the observability function. What I like to mention in this page is the amount of Lie derivative that we need. There is no real explanation or any given idea how many Lie derivatives are necessary for a given nonlinear function. This depends on the function itself. So the amount of Lie derivatives may vary with a function, and I would like to show this on a simple example. Let's consider this system here. And if we compute the Lie derivatives, then we first notice that the system has the dimension 2. So if we compute the first two Lie derivatives, which are shown down here, and compute all solutions for these two equations, then we get by side the trivial solution, another set of solutions. So currently the set M is bigger than the set D because of this additional solution. And therefore this nonlinear system is not observable. If we take the next Lie derivative into consideration, then the set that is here additional sizes down to a single point, but still the system is not observable. Only if you take the fourth Lie derivative into consideration, then the only solution which fulfills all four of this equation is only the trivial solution, and therefore now the set M is equal to set D, and therefore the system is distinguishable and therefore global observable. So that means we have to compute the Lie derivatives, and we could maybe compute or write a program and pre-calculate every Lie derivative, implement them. And since we don't know how many we need, we also could, of course, try a given amount, which seems to be enough. If this is not enough, we could always calculate more Lie derivatives and try the program again. However, the problem with the Lie derivatives is the structure how the Lie derivatives are calculated. To get the next Lie derivative, we compute the previous Lie derivative and multiply the system function on it. If the system function of a nonlinear system is quietly more complicated than this one, then this leads to the effect that the Lie derivative itself explodes in length. And this is shown by the next example. For this almost quite easy nonlinear system, the fourth Lie derivative is such large that it doesn't even fit on the slide. And from that point, the problem only gets worse. So if you try to implement such long equations, for example, in MATLAB, you will very shortly find out that there is a limited amount of characters you can put into a line. And MATLAB doesn't like to compute with such long equations. Also a C++ compiler, I've tried it with an even longer equation, took over half an hour to compile the program, and then it just crashed with an error. To still use the Lie derivatives, we need a different way to compute them. And the way is by using the power series. There we have this base object in this form, and this comes with some calculation rules. For example, for the multiplication, we use the Cauchy product. Now we can define, for example, x according to this base object, that this depends on some coefficients xk, and also for f, we can also construct this in this way, so with the coefficients fk. Now we can use this formula here to compute every further xk plus 1 that we need by using fk, and fk we get by evaluating this system function with every coefficient that we already have from x0 to xk according to these rules when we evaluate the system function. If we compute enough of our coefficients, then we can use them to calculate the coefficients hk, and these correspond with the Lie derivatives. If this may sound confusing, I will explain it with a short example. Let's consider this nonlinear system, and we have the starting point at x0, which be the first coefficient x0, which is 2 and 4. If you want to compute your Lie derivatives, we have done this here analytically, and here are the solutions for these Lie derivatives. Now we want to reproduce this solution with our power series. The first one is very simple. We only have to insert this into the output function and get the solution. For the second one, we have to use the calculation rules of our power series. And first we have to calculate the component x1 with this equation. And therefore we have first to calculate the solution for f with our 0th component, and we get the solution for our x1 component. This is 4 and 14. Now we have all the components we need to calculate the h1 component by inserting this x0 component and this x1 component into h in the function and use the calculation rules shown before. By using the addition, we have to compute the one component of x1 plus the one component of x2. For the one component of x2, we can write this as a multiplication of x2 times x2 times x2, and then we can use the Cauchy product to evaluate on that. So that is the 0 component of this bracket multiplies with a 1 component of x2, and then plus the 0 component of the second part multiplies with a 1 component of this bracket. And this is again a multiplication, so we use the Cauchy product again and get this equation here. While this may be quite complicated to compute this by hand, it's very easy for a CPU to compute this, since it only have to follow certain calculation rules. And we also can use the interval arithmetics and also automatic differentiation with this, and use the operator overload for the power series and compute everything in one go. So now we have all basic tools that we need for the algorithm. And for now, I've got this definition for an interval. This is only to show that x with an upper letter I just means that this is an interval. And let's consider we have a nonlinear function which we want to evaluate if this is observable on a given initial state dx. Then, for example, we can multisect this initial state into many smaller intervals. And let's say we want to identify if the red interval is global observable on this initial state. So we use our distinguishability condition here for this interval with every single other interval and test wherever the intersection of this is the empty set. If this is the case, the interval stays gray. If the intersection is not the empty set, then this interval becomes blue. So a possible solution might look like this. Now we don't do this only for this one interval, but for every other interval in the algorithm, and sort this into a list structure and store it. And in every next iteration, for example, we could bisect this interval and therefore reduce the overestimation and maybe exclude some of these outer intervals. But it is also quite obvious that no matter how far we bisect this interval, we will never get rid of all of these blue intervals, because, for example, two neighboring intervals, the above one and this one, have a common edge. And by mapping these intervals, we also have a common edge. And with using the interval arithmetics, we have this overlapping area. Therefore, the set will never be the empty set. To deal with this problem, we use the local condition. What we've done now is we've shown that the red interval is global observable or distinguishable to every interval outside here, so every gray interval. We can only not distinguish the red interval from this blue one, so we size the problem down from a global one to a local one. If we now build the hull of these intervals and can show that the hull is full of rank in our observability matrix, then that means that the red interval is local observable in its local area and also global observable on the global area of dx. So we have first to compute the interval observability matrix by computing the Jacobian of the observability function. This can be done by automatic differentiation. And now we only have to show that the local condition is fulfilled. That means that this interval matrix is full of rank. This could be possibly checked by computing the determinant. However, the determinant for this interval matrix is very overestimated, even for a 2 times 2 interval matrix. Another method would be computing the eigenvalues. The eigenvalues can be computed by the theorem of Rohm. This gives an enclosure of the eigenvalues, and it works by computing the eigenvalues of a midpoint matrix and subtracting the spectral radius of the radius matrix for the lower estimation, or adding the spectral radius for the upper bound of the eigenvalue. to compute the eigenvalues, our matrix must be a quadratic one. But we change the amount of Lie derivatives described by kappa, and therefore our matrix Q is probably not a quadratic one. So we first have to force it into a quadratic form by defining this vi. And now this matrix is now a quadratic one, and we can compute the eigenvalues with the theorem of Rome. And since it follows that kappa p is always bigger n, because we choose kappa to be bigger than n, therefore it is necessary to prove that 2n of these eigenvalues does not contain 0. So we can adjust the theorem of Rome for our purposes in a way that if the amount of eigenvalues that does not contain 0 is equal to n, then we can show that our matrix Q is full of rank, and therefore the interval is local observable, and previously we already showed that is distinguishable in a global scale. This we can now, what I would like to talk next is the amount of Lie derivatives that we need. And the algorithm always computes one Lie derivative more than is currently necessary and checks this global condition and the local condition for these three cases: for kappa minus 1, but only if this is still bigger than n, for kappa and kappa plus 1. If one of these conditions is fulfilled for kappa minus 1, then the algorithm decreases the amount of Lie derivatives. And if these conditions are only fulfilled for kappa plus 1 or none of these, the algorithm increases the amount of Lie derivatives. And therefore, the algorithm can adjust the amount of Lie derivatives necessary and dynamically. And this we can see in the next example. This example we already proved analytically that this is global observable. And given this to the algorithm with the set that we are interested in, we got this output by the algorithm. Here we can see every interval for which observability could have been proven. And also these are color-coded. So the dark squares are where the algorithm needed less Lie derivatives, and the brighter ones are those where the algorithm needed more Lie derivatives. We can see here on the outside that we have some intervals that are quite large and need a low amount of Lie derivatives. And here at a point of -1/2 and 0, this was the point that was troublesome for proving the observability analytically. We see that the algorithm needs to bisect the intervals further and calculate more Lie derivatives. Another example taken from the literature is this nonlinear system. The literature says that this nonlinear system is probably not observable. The algorithm also couldn't find a single interval for which observability could have been proven, but the algorithm delivers even more than that. What we can see on the right-hand side here is the same that I used to show you the function of the algorithm. Here are shown all intervals that are indistinguishable to one single interval. The one single interval that is somewhere inside this donut, it's the red one, but it's covered by the blue one, so we cannot see it. With this data, we can evaluate why the system is not observable. In this case, it seems that the quadratics of the output function are an issue. If we remove them, we get a different picture. Now we can see all intervals for which observability could have been proven. And we also see more than that. We can see that x1 and x2 are quite small compared to the initial area, while the third state, x3, is on the full length of this initial area. That means that x1 and x2 seem to be some cylindric component that comes here into this result, and x3 is not an issue for the observability, and we can get an insight how to enlarge this area of observability where we can prove it. Now, the next thing I would like to talk about are the uncertainties. We have here another example with an uncertainty A. also taken from the literature. And every step I've shown for now is also capable of doing this if this uncertainty is given by an interval vector. We can compute everything with this interval vector. And the only change we are doing is we don't only bisect in x1 and x2, but also in this uncertainty. And with that, we get the result by the algorithm that all intervals for which observability has not yet been demonstrated lie within the interval uncertainty of this one. So that basically means that this nonlinear system is observable if the uncertainty is not in the near of 0. Only for coefficients near 0, this is not being proven to be observable. And the algorithm is also capable of dealing with these uncertainties. And with that, I'm at the end of my talk. Thank you for your attention. And here also the reference is shown throughout the talk.
Okay, many thanks, Thomas, for your nice presentation. And also your talk is now open for discussions. Okay, do we have anyone in the audience who wants to start? Yes, Luc wants to start.
Okay, thank you. On your, thank you for your both nice talks. I would like to go to the previous slide from this one, if possible. Yes, this one. So here, A corresponds to alpha. Yes, it's the same. No.
Alpha is just the uncertainties. This can be of an arbitrary length, and
okay.
The uncertainty in the literature is called A, and I keep the notation of that.
Okay, so A is equal to 0. A is constant, yes?
If A is equal 0, then this is probably not observable.
Yes, but A dot, the A is constant, it does not depend on time, yes?
Yes.
Yes, so you can put it as maybe as a state variable, and then you are inside the framework of, you are in the situation where you have no uncertainties as you have done previously, no? It's not a special case of what you have done before. Since NA can be seen as a state variable with A dot equal to 0, no?
This would be possible, yes.
Okay, so why you deal as a special, I don't understand why you made a second part with uncertainties if it is a special case as what you have done before. No, I don't understand this.
It's to show that if we, for example, are in the early stage of an evaluation of a plant, for example, where we have a system and we are not certain about the parameters and want to know if it's still observable, then it is a constant and it also works with the constant. And of course, if A changes slightly, then you don't need to really evaluate this as a system or as a function.
Okay, thank you. So I have another small question. In the here you deal only with probably local observability, no?
No, it's also global observability because
it's global observability. So what I don't understand here is maybe in the previous slide when you show different subpavings in the previous slides. Yes, like here. So I don't understand how you succeed. You only have to bisect on the x1, x2, x3 space, or do you have to bisect on so here it's a 3-dimensional space. You don't need to bisect on the 6-dimensional space in the cross product of a 2-vector space. Maybe you understand what I mean. Here you only have to show the global observability. You only have to bisect on a 3-dimensional space. It's sufficient. Okay, I thought it was you had to bisect on a 6-dimensional space. In the so it's okay. So you succeed to do this.
It's maybe a little confusing when I say global observability. What I mean by global observability is always on the initial state dx. Of course, I don't know what's outside, and by bisecting this initial state and by using the distinguishability. This was the global condition. We show that, for example, this interval can be distinguished by this interval. And this gives us the global case, and we only cannot distinguish, for example, this interval by its neighboring intervals, and there we use the local condition.
Okay.
So we get the global observability by proving or showing that this interval can be distinguished, for example, by this interval.
Okay. Thank you very much. Thank you for the answers. Thank you.
Thank you too.
Okay, I think the first question of Luc gave me something that I wanted to ask. When you're extending your state vector by a further uncertain parameter, time constant, new state variable, I think you're proving the observability of the parameter itself. And the other thing, what you did is when you're plugging in an interval bound for your parameter alpha or a, in this case, I think you're proving observability for the union of all realizations of this parameter. I think this is slightly different.
Yeah, this is also true, because if we get this as a constant, then we don't have to deal with a problem that, for example, if we have -1 and 1, we don't need to verify that this is observable if R is -1 and also 1, because it can only be either of these.
Mm-hmm.
But we still show that, well, in this case, it's not observable if it's near 0, but we can show every other parameter that's not inside this bounds can be observable. So if this is a plant, for example, if A changes very slowly, so for example, this is the parameter which changes very slowly over time, then we can still use this as a constant, because we can show that if A is -1 and then becomes, for example, slowly -0.5, it still will be observable.
Okay. Before I hand over the microphone to the rest of the audience, I have a further question. Namely, you mentioned in your abstract of today's presentation that you're using also the conditions for an optimal sensor placement. And maybe you could elaborate a little bit more on this.
Yes, I haven't talked about this. That's correct. It's not that this algorithm gives you directly an optimal sensor placement or how to modify your output function in a way that you have an optimal sensor placement, but you can use this algorithm as a try and error method, where you can try a sensor configuration of your choice and test whether this is observable, and then try, for example, another configuration, and then maybe find a way where you can use less sensors to be, well, so that your product is not that expensive, or in any other case. So it's not that the algorithm delivers automatically something like that, but you can use it in a try and error case.
Okay. I think this was also interesting for the audience, because I know you recently, I'm not sure if this was in the list of references that you gave at the end, but you recently published a paper in the journal Algorithms where you also mentioned this a little bit. Maybe if it's not given on the list, you could add this reference.
It's not given in this list, but here only the one that I mentioned throughout the talk. And yes.
Okay.
Yep.
Do we have any other question from the audience? Yes, Peter, please go ahead.
Yeah. So, well, first, thanks for two very nice talks. One question is, so as far as I can see, you only prove observability, and my guess would be if the system's unobservable, then you can't use interval methods to prove this. You can only use algebraic methods. Is that correct, or do you also see the possibility of using interval methods?
No, this is correct. We cannot prove that the system is not observable. We can only prove that some parts of the initial interval vector are observable. And for example, in this case where the system is probably not observable, we also couldn't find any interval, but that doesn't mean anything, because maybe we didn't have tried enough Lie derivatives, and if we maybe calculate the 1000 Lie derivative, we maybe find an interval that is observable. So of course we cannot show that it is not observable, but we can show that is not observable with the amount of Lie derivatives we have calculated. And if we go far enough, it is not a 100% sure answer, but it's probably not observable, at least it is troublesome.
Maybe I can comment on that also a little bit, if you allow.
Of course.
If you look into my presentation, if the system is not observable, that means you can find initial conditions which are not equal to each other, which have the same image under this mapping capital F or small q, what Thomas called it. And that means you have to find a solution to a set of an infinite number of equations and prove that that solution is given. And I think you are right, completely right. That's impossible to do with interval methods. That can only be done by algebraic methods. For example, Thomas has in his citations one of my papers where it is shown for polynomial systems how that can be done.
Okay, yeah. So you said, so it's decidable for polynomial systems, is it?
Yes, it's decidable.
Is it known if it's decidable? Okay, okay.
It's decidable because for polynomial systems, this can be reduced to an ideal intersection, and that can be done in a finite number of steps. This is part of, I think Hilbert already proved that, or Eminöter. So for example, with Gröbner basis algorithms and some things, you can prove that. You can really compute the,
okay,
you can compute all pairs of unobservable states doing that. It's explained in this paper from, I think, 2002 or so. Oder Herr Paradowski, vielleicht können Sie die Literaturliste kurz zeigen.
This one.
It's paper number 2. For a simple example, it's shown how that can be done using reduce. Today, one would use Singular or Maple to do those computations. But this only works for polynomial systems because the ring of polynomials in n variables is Noetherian, and if you have real algebraic analytic functions, then the ring of analytic functions is not Noetherian. That means not every ideal is finitely generated, and that's the main obstacle in that case.
Okay, further questions?
Yeah, Peter has a question. Or?
I think, Peter, has your question been answered with that?
Yeah, my question's been answered.
Okay, because you still raise your hand. Okay, do we have any other questions from the audience? Maybe one final question from my side. I think currently you have implemented, at least as far as I know it from your PhD thesis and also from your journal paper, you have implemented the algorithms totally by using CPUs. Where do you see possibilities how to parallelize this massively using GPU-based computations?
It may be possible to calculate this one somehow more efficient, and yeah, maybe this is a opportunity to use this and accelerate this algorithm.
That means your coefficient-based evaluations of the Lie derivatives would be evaluated massively parallel for a large number of interval boxes at the same time.
Yes.
Okay. So, any other questions?